So let's look at this example. Let's look at, sure, f of x, y equal to 6x squared plus 6y squared minus 3x squared y minus y cubed. Yeah. They all sort of look the same. You're like, this one looks like the one I already did, but it's not. Okay. So we're going to find the critical values the usual way. And then after we find the critical values, we'll talk about how we can determine whether we have a maximum or a saddle using the other method that's being done in Casal's class. And Caleb, do let me know if you're in. I just want to make sure that we're not confusing you if you're not in Casal's class. So let me know whose class you're in when you have a second. All right, so critical values, taking those partial derivatives and setting them each equal to 0. Just want to point out again, right? This is really setting the gradient equal to 0. So this fx, fy, that really is the vector that is the gradient. And so when you're setting that equal to 0, you're setting the gradient vector equal to the 0 vector. Okay, so all right, fx is 12x minus 6xy. And then fy is going to be 12y minus 3x squared minus 3y squared. And clearly, to me, it seems like the first one is actually going to be easy to find some actual values for x and y. So from this first one, I'm going to factor out a 6x and be left with 2 minus y. I'm going to get x equal to 0 or y equal to 2. And then from the second one here, setting or plugging in either of those. If I plug in x equal to 0, I'm going to get 12y minus 3y squared equal to 0. Factor out a 3y, and you're left with a 4 minus y. So we end up getting y equal to 0 and y equal to 4. So the two critical points from that part are 0, 0, and 0, 4. Now, if we set y equal to, I should point out, sometimes when you do this, like you could set x equal to, you could set x equal to, I don't know, sometimes when you do this, you like plug in one of these points, the other equation becomes unsolvable. Like you could plug in x equals 0, and the other equation could be y squared equal to -9. And so you just don't get any critical points from there. Sometimes that happens. So if we set y equal to 2, we're going to get 24 minus 3x squared minus 6 times 4 is 12. 0. And so you've got, I'm just going to factor 12 minus 3x squared equal to 0. So 3 times 4 minus x squared. So you get x equal to plus or minus 2. So you get 2 comma 2 and negative 2 comma 2. So those are 4 critical points. And then I have to look at the notes here because I don't actually, I mean, I kind of know what's going on. Oh, wow, those are not the notes I meant to click on from his class. I clicked on practice problems, not notes. I see. Okay. So then what we're going to do is we're going to find, yeah, it seems like way more work. Like, right, because you have to find, I mean, I guess it's technically the same. No, it's more work. It's more work. Okay, but I guess there's more understanding here. So we're going to find the general recipe here where A is equal to fxx at your point, B is equal to fxy, C is equal to fyx, D is equal to fyy. Yeah, wow, interesting. Yeah, I might as well show you what's actually going on, because here's what's happening. So the reason we are talking about this is because, in fact, he even said these words. I think he said these before. When you're evaluating these critical points, you're actually finding the determinant of the Hessian matrix, which is exactly this fxx times fyy minus fxy times fyx, but they're the same. So we just write fxy squared. But that's really equal to, I'm going to write this down, just hold on. This is the determinant of this 2x2 matrix. fxx, fxy, fyx, fyy. And just so you know, because you're going to be doing it eventually, probably, When you take a determinant of a 2 by 2 matrix, it's just the product of the diagonal elements minus the product of the off diagonal elements. And so that's why he's writing this. He's thinking of this as the matrix A, B, C, D, because then when you take the determinant of that, you just get A times D minus B times C. Okay. So then, yeah, I mean, I guess that works, but it just, so then he's saying we want to find the characteristic polynomial of this matrix, which is the thing we do in linear algebra. And so here's what he's actually doing. He's saying, I want to take the determinant of this matrix, A minus lambda, B, C, D minus lambda. That's what's actually happening here. And look what happens when we do this. You get exactly A minus lambda times D minus lambda minus B times C, which might not look all that exciting at the moment, but, well, I mean, it's not, okay, exciting might be a strong word to use here, but look what this is going to turn into. I'm going to get A times D minus lambda D minus lambda A plus lambda squared minus B times C, or rewriting this another way, lambda squared minus A plus D times lambda plus AD minus BC. And just for full transparency here, A plus D is called the trace of the matrix. And the trace is just the sum of the diagonal elements of a square matrix. It can be any size, it can be 3 by 3, 4 by 4, whatever. You're just adding up all the diagonal elements. And then this thing here, that is your determinant again. That's your A times D minus B times C. That's the determinant of the matrix A, is what we usually call that. This is the trace of the matrix A. We're calling this the matrix A because that's what we're calling it. So that's where all this is really coming from, in case you wanted to know. If you didn't want to know, well, now you know anyway. And so then he's saying, well, to classify what's going on, it's still like, God, it was still a giant pain in the butt, though, because you have to evaluate each of these for each of the critical points. Yeah, that's not in love with it, gotta say. Yeah, interesting. Okay, so I apologize. I just can't make, I'm trying to find a justification for why you would ever do it this way, and I cannot see it. It just seems like more work, but let's do it anyway. Okay, so we've got our critical points, and let's try and at least be systematic about it. So we're gonna make a table like he would. We're gonna do this my way too, just because I think we should. So we've got our critical points here, x naught, y naught, and those are gonna be 0, 0, 0, 4, and 2, 2, and -2, 2. And then we've got our A, B, C, and D. But I guess I didn't actually find my second partial derivatives. So maybe I should do that. So fxx is going to be, let's see, I'm looking over here, fx on my page. That's going to be 12 minus 6y. And fxy is going to be -6x. Sorry, I should probably show what I should show what I'm referring back to here. And so my fx there was 12x minus 6y. So there's my, I really wish the sun wasn't over there. I mean, I was like, here's a big shadow on everything. Or I guess it'd be good to be left-handed right now, but not so. Oh well. Fxy is -6y, -6x, sorry. Fyx should be the same, and it is. And fyy is going to be 12 minus 6y. Okay, that's not too terrible. You good on that? Okay. So now we're going to find A, B, C, and D. Great. Seems brilliant. Okay, so plugging in 0 here, I get 12, 0, 0, 12. And then we're going to find the characteristic polynomial. Yep, sure. Okay, so it's going to be lambda squared minus 24 times lambda. And if one of your roots is 0, I think it's yeah, this is not helpful, because I know I know based on the work we've done that if I got these values, I'd be getting 12 times 12 minus 0, which is positive, which means we have a max or a min. Since both of those are positive, we know it's concave up, so it's a minimum. This, according to what he's written here, the minimum of both roots are positive. It's a maximum of both roots are negative, and it's a saddle if one's positive, one's negative. But killing me. Killing you. So the roots are 0 and 24. So I'm curious. Maybe it's really if one of the roots is positive, if both roots are greater than or equal to, if at least one is positive and the other one is non-negative, maybe that's all you really need. I don't love this. Okay, anyway, so let's look at the other roots and see what's happening here. So here for 0, 4, y is 4, so we get 12 minus 6, 12 minus 24, which is negative 12. And then we're going to get 0 and 0 and a negative 12 again. And we're going to be left with the same exact problem. Lovely. Maybe I did something, oh, you know what? I might have, I might have led you astray here. Not so far astray, but I might have been in the mindset of doing this when I really should have been doing this. So let's double check my determinant here, because I think I might have done that wrong. So I think this should actually have been, let's see. So I'm just throwing these things into this formula. Okay, it seems super dumb. Oh yeah, okay. I was making a mistake there. It's not quite as terrible as I was pretending it was. Sorry. So really we should have had lambda squared minus a plus d, and then plus a times d minus b times c. So plus 144. Okay, fine. So that's going to factor as lambda minus 12 squared. And since both roots are positive, we have a minimum. Okay, here, same deal, except we're going to get lambda squared plus 24 lambda plus 144. So then we're going to get lambda plus 12 squared. And so we're going to get both roots being negative. So we have a maximum. Okay. I bet these last two are going to be saddles. Well, we have to check. So plugging in 2, we get 0, negative 12, negative 12, 0. And then, holy smokes. So then my character's polynomial is going to be lambda squared plus a plus d is 0. So I get 0 lambda, and then plus a times d minus b times c, so minus 144. So there my roots are going to be positive and negative 12. So we have a saddle. And I bet we get the same thing for this next one. Because we have negative 2 and 2, yeah, we're going to get 0, and then b is going to be positive 12, 0. So we're still going to get lambda squared plus negative 144. And that still gives you the same. Holy smokes, that is terrible. Sorry, not to be over dramatic about it, but like I don't see the value in doing it this way. Other than it is interesting. It's giving there is, I mean, he is literally talking about, like, because this formula comes from finding the determinant of the Hessian. But we have in some sense tried to make it easier by saying, instead of having to do all this, there is an equivalent alternative condition, which is that, well, in fact, so how deep do we want to get into this? So here's what I'll point out here, right? Instead, so how do I say this the right way? How do I say this the right way? I mean, really, it boils down to like getting into the quadratic formula. You could, but yeah. So, or we could have just looked at this. So let's just contrast this because I think it's worthwhile. So in this case, it's going to be 12 minus 6y times 12 minus 6y minus, what is it? fxy is negative 6x squared. So here, if we plug in 0, 0, we're going to get 12 times 12 minus 0 squared. That's positive. And then we say, okay, great. fxx was positive, so we have a minimum because we're concave up. It just feels like so much less work. Yeah, I don't know. I don't like, so you could definitely, we could talk about how these things are equivalent. I don't think there's a lot of value there. I guess I would maybe ask what his expectations are as far as how you actually do this, because the book, I believe the textbook does not do this, although I guess I should go look to be really sure. I'm fairly confident the textbook does it the way I've always seen it taught before. So yeah. Should we practice another one though? Yeah, just in case. Yeah, I would agree. Right. Yeah, like, but I would definitely, because right, I mean, there are other ways of doing this that are always correct. Yeah, they're correct. And yeah, good times. Okay, so let's look at something like, sure. I don't know how, I'm just grabbing ones here from previous problems. I don't know how this one's going to go, but let's take a look. Now I'm definitely now I have to go look up the like how they actually, because the thing that we are doing, I'm sure, is derived from this in some way. But yeah. Thank you. So let's find our critical values. X is going to be 2x plus 4y. Fy is going to be 4x plus 8y cubed. Okay, interesting. So then I'm definitely going to deal with the first equation, I think. Yeah, probably. I'm going to write this as 2x equal to negative 4y. And really, I'm just solving for the one that's slightly, like, I would rather say x equals negative 2y than y equals negative 1/2 x. Now, maybe looking at where I'm going to have to plug into, I might make a different choice, but no, I don't think so. I would rather plug in for x than plug in for y. So I think this is the right choice on both fronts. So from here, we're going to rewrite this as 4 times negative 2y plus 8y cubed equal to 0. We're getting negative 8y plus 8y cubed equal to 0. We're factoring out, let's factor out a negative 8y. We're left with a 1 minus y squared. So we're getting 3 values of y here. We're getting y equal to 0, y equal to 1, y equal to negative 1. And then x is going to be, well, if y is 0, x is 0. If y is 1, x is negative 2. Y is negative 1, x is positive 2. So there's our critical points. I guess we should prepare to make the world's worst table. Sorry, I don't mean to sound so judgy, but I am. 0, 0, 1, sorry, negative 2, 1, and 2, negative 1. Okay, so then we have to find all the second partials. And we should label, yeah, labeling too, okay. It just feels like so much to memorize as well. Like we're taking the stuff that we were doing and then adding on a whole other thing on top of it that seems unnecessary. Okay, enough ranting, just deal. So A is going to be fxx, which is going to be 2. Great, we don't even have to plug in for that. That's going to be awesome. B is going to be fxy, which is going to be 4, which is also going to be c. If your function looks normal, meaning it's just like powers of x and stuff, there isn't any weird piecewise stuff. If your b and c values are not the same, if your fxy and fyx are not the same, probably means you've made a mistake. So go back and check. And then finally, our d value is going to be fyy, which is going to be 24y squared. So this one isn't terrible in that you only have to plug in for one value here. So our A, B, C, and D. Really, we should just write ABC is going to be always 2, 4, 4. And then our D value is going to be 24y squared. So 0, 24, and negative 20, positive 24 still. Okay, cool. Characteristic polynomial, which I guess I kind of remember. Lambda squared minus A plus D times lambda plus AD minus BC. Okay. So we're getting lambda squared minus 2 lambda plus AD, which is 0, minus BC, which is 16. So minus 16. But that doesn't, then you have to use the quadratic formula. Yeah, geez. So then we use the quadratic formula and we get lambda equal to 16 plus or minus the square root. Now we don't actually have to calculate it. We just have to be able to see if the roots are going to be both positive or both negative or one of each. And if they come out imaginary, then you should just cry. So we get B, but they'll never be imaginary if this part's negative here. So let's see, 4 minus 4 times 1 times negative 16. All over, doesn't matter. Okay, so inside the square root, I have 4 plus 64. And so that's like 68. Now here's what we have to observe. Is the square root of 68 bigger than 16 or less than 16? Definitely, right? It's pretty close to 8. So 16 minus it is still positive, and 16 plus it is still positive. So they're both going to be positive. Or lambdas are both positive. So that's the idea if you're using the quadratic formula. You just have to be able to tell, is the thing you're adding or subtracting here bigger than or less than the thing you're adding over here? If it's bigger, not in this case, but if this had been bigger than that, then you would be getting 16 plus something bigger than, which is still positive, and 16 minus something bigger than, which is negative. And so then you're getting a saddle because you have two opposite signs. That's the whole kind of story here. Okay, let's look at this next one, which hopefully is not as terrible. Well, both of these are the same though, at least. So it's only one thing with a work. Lambda squared, and then A plus D is 26. Not bode well. And then minus plus A times D, which is 48, minus B times C, which is 16. 48 minus 16 is 32. Mother. So good. Yeah, I don't see how to multiply the 32 and add the negative 26. I don't think. 16, no, 16 and 2. Nope. So fine. Now my guess is they're going to be saddles, just because it often seems the case that when you get two different critical points that came from like the same thing, like it's like X is plus or minus this and Y is that plus, like it kind of feels like those often end up being saddles. I don't know why. It's having seen it many times. That's where my intuition falls. That usually ends up being a saddle. Okay, so we're getting 26 plus or minus the square root of 26 squared. Okay, so here's okay, fine. I guess they're not going to be. We're gonna have to check this the other way, because you get 26 squared minus 4 times 1 times 32. And here's what I would point out. I don't need to do any more calculation here, because I know that this number inside this square root is for sure less than 26. Because you're taking 26 squared, you're subtracting some stuff, and then taking the square root of it. Right? It's got to be less than 26. Convinced? It's a negative b. I love this formula. It's so my favorite thing ever. Okay, sorry. So looking at this one for a second. Yeah, we need to go back there. But looking at this one just for a sec, these are actually not saddles, right? Because 26 squared is a number. It's what? It's 625 plus 25 plus 26. It's 676. But then you're subtracting off something. And then if you take the square root of that, well, the number is less than 676. So its square root is less than 26. So you have 26 minus a number smaller than it, which is still positive, and plus still positive. So these lambdas are both positive. So here we have both of these are actually minimums. Yeah, minimums. Okay, so let's go back to 0, 0. Oh my God. Holy smokes. So we're really, actually, it's not that different though. It's just going to be 2 plus or minus the square root of 68 all over. It doesn't matter. And so that's actually going to be a saddle, right? Because you have 2 plus something larger than it, positive, 2 minus something larger than it, negative. So here our lambdas are opposite. One lambda is positive, one lambda is negative. So we have a saddle. Let's graph this thing. Just because I'm pretty sure this one looks pretty neat. And also because it's nice to see that the thing is actually the thing we said it was. Let me just type it over here because it's easier to type it over here. Okay, so we've got z equal to x squared plus 4xy, and then plus 2y to the 4th. Ooh, yeah, it's cool. Kind of looks like a pair of pants, right? You've got your 2 minimums there. I mean, pants that you cut off the bottoms to make them actual pants. But yeah, you got your 2 minimums and your 1 saddle point there. Kind of cool. Not from that angle though. Anyway. Okay, so that works. Good God. So if it were me, if I were you, I would look in the textbook and verify first. I'm going to look anyway, but that the way we have been doing it in class is also a way that is valid. And then maybe ask, like, this way is totally fine, but would it be okay if I did it this other way on the exam, which is way, in my opinion, easier to do? I don't know. That's what I feel like might be. If you are comfortable doing that, I would encourage it because it seems like just so much more work this other way. Especially when you're especially when you're throwing in the quadratic formula there. It's just like it's too much to do for one thing. Yeah. It really is, especially on an exam, right? Like I could see him asking a question though, like if he really wants to make you do it this way, ask you to be like doing it piece by piece and be like, what's the characteristic polynomial and what are your so it might be unavoidable. All right, sure. Let's kind of I would say let's talk review a little bit in that. Let's kind of just talk about the highlights as far as what I would imagine you're probably seeing on your exam. We'll start from the beginning. So here I would say topics to focus on for your exam review. And again, this is all maybe under the caveat of whatever he says should supersede this. So here's what I think, but if he said other things, let me know. Like, what did he say about review today? Or did he just start doing? I don't know. Sure. Okay. Okay. All right. So yeah, so I could see series being kind of a big deal. All your tests for convergence or divergence. Intervals of convergence. So for convergence, divergence, right? There's a lot of tests, and there is a handout on Canvas that kind of shows all the tests as a flow chart. But we've got, the integral test, which I feel like is probably the one you use the least. You've got the ratio test. You've got the root test. You've got the nth term test, which is only for divergence. Also called the test for divergence. Yeah, got the alternating series test. I feel like I'm forgetting one. Oh, the comparison tests. Both the direct comparison and my favorite, limit comparison. And there's certainly times when certain tests are better than others. Integral test, I think, is obviously the best if you see it's something you're able to integrate and can't think of another way to do it. It's usually kind of the last test we're going to use for a series though. Ratio test and root test. Root test specifically, if you have everything raised to the nth power. Root test is if you have some stuff raised to an nth power, but some other pieces as well. So you have like an nth power and or a factorial. Ratio test is like factorial automatically ratio test. Nth term test kind of should always be on your mind if you're looking at the series, right? You're always checking to see, does that limit of my sequence actually equal 0? Right? Because if it doesn't, then your series diverges automatically, you're done. Alternating series test, obviously if it's alternating. And then direct comparison, limit comparison specifically, I would say you use when you have the sum of a rational function. So some polynomial over some other polynomial, except the polynomial is an n, not x, but you get the idea. Right, so specifically if you have something like that, that is where you want to use the limit comparison test. And so for example, if your summation was like the sum from n equals 1 to infinity of, I'm just gonna make up something like 5n to the 4th plus 6n squared plus 1 over 2n to the 7th plus 5n to the 6th. You would want to limit compare this with the sum of n to the 4th over n to the 7th, which is just 1 over n cubed, which means we are trying to show convergence because we're comparing it to something that converges. And then, yeah, those are mostly all the tests. And then we have like power series, Taylor series. If I were looking to ask a question about power series or Taylor series, I might ask a question about like finding the interval of convergence. So finding the interval of convergence for something like sum from n equals 1 to infinity of x minus 2 to the nth power over 2 times 3 to the n. 2, do I want that 2 there? Yeah. I want an n there really. N times 3 to the n is more interesting. 2 is kind of dumb. So something like that, where you would use the ratio test and set your limit to be less than 1, and then you have to test the endpoints typically. And then the other thing I can see maybe asking about is using a known Taylor series to find something new. For example, like using the Taylor series for sine of x. So use sine of x Taylor series to find x cubed times sine of x squared. And so that's where you definitely have to know, and you should know, e to the x, sine of x, cosine of x, and 1 over 1 minus x. There are other ones you could probably make arguments for knowing, but those 4, if you're going to know any 4 Taylor series centered at 0, those are the 4 you should know. I think anyway. I feel like there's something else to say here. I don't remember. Did he talk about in this class usually finding like derivatives and antiderivatives of power series? Yeah, that seems weird because usually I feel like that gets covered. Interesting fact. When you do differentiate or anti-differentiate a power series, the radius of convergence doesn't change. which is kind of interesting. Yeah, that does seem strange now that I mean, I guess it's not really on. Yeah, it's not really on the syllabus. But yeah, that seems bizarre. Okay. All right, so then that's the series stuff at a kind of a wide view. I think on Wednesday we can do more sort of specific review of things. He's posted the practice final. Okay, cool. So I'll look at those and maybe we'll go over one of them. Maybe I'll just make up some stuff, but we'll try to have a good kind of idea of what we're gonna look at. So that's kind of chapter 10 in a very, very brief nutshell. And then we have the chapter 12 stuff, which is all like the vector stuff. The vector stuff. Or as I like to say, distances between things. Because I feel like that's most of what this chapter is about. Like you're finding distances between a point in the line or a point in the plane. So, right, I mean, stuff I think that's barely bears mentioning just because you have to know this stuff by now. Dot product and cross product, right? They're just, we use them all the time in this chapter. We know how to calculate them. Something important to know. Ooh, yeah. So dot product, right? So just one thing, right? If u dot v equals 0, then what do we know about u and v? Right. On the other hand, if the cross product of two vectors gives you the 0 vector, yeah, they're in the same direction. They're parallel. I should say, really, they're in the same or opposite direction, right? They could be pointing both in the same direction, or they could be pointing opposite, meaning u parallel to v, or you could say u is equal to some multiple of v. That's another way of saying vectors are parallel. And that multiple can be positive or negative. If it's positive, same direction. If it's negative, opposite direction. Yeah. And I guess it's, so we should know how to calculate the dot product and the cross product by just doing it the easy way. But it's also important to know that u dot v, the v, is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. And then, at least from that practice test we looked at one time, it's also good to know, apparently, that u cross v is equal to the magnitude of u times the magnitude of v times sine of the angle between them times a unit normal vector in the direction of the cross product. We don't almost ever actually use this, but what we can use this for is to then kind of calculate the magnitude of that cross product. Right? Because if you want to find the magnitude of u cross v, sorry, sometimes I use the double notation, sometimes I use the single. I don't actually know why I do one or the other. It's the magnitude of u times the magnitude of v times sine of theta times 1. So that's kind of useful as well. And then, yeah, lines and planes. So I never remember. I can never, it honestly, like, it just escapes my brain every time what the formula is for the distance between a line and a plane. I think I might finally have actually memorized it, but I feel like, so here's what I would say. As far as distances go, a point to a line, that's the sine one, that's the cross product one. That's the cross product one. So, right, here's your line, here's your point. We like to call this point S, we like to call some point on the line P. And the thing you have to remember is that the vector you're crossing with is just the vector that's the direction of the line. So this line goes in some direction, V. And so this is going to be PS crossed with V magnitude divided by the magnitude of V. And then for a point to a plane, it's the same type of equation, except with the dot product instead of with the cross product. Which I wish I could fit here, but I feel like I can't. So point to plane, same idea, but now it's going to be the dot product one. By the way, I should just point out, it totally makes sense that this one is the cross product one. So if you think about dropping this perpendicular here and then using that angle there, you're definitely using sine of that angle to find that distance. For the point of the plane one, it's always hard to remember how you're supposed to draw the picture. At least it is for me. So same idea. There's your point S, there's your point P. Here's your normal vector. How do you get the normal vector? If you know the equation of the plane. I know I'm asking the question like there's lots of people in the room, but Madison, how do you get the normal vector if you know the equation of the plane? Let me give you an example. Let's say the plane, you actually use like symbol pi for the plane, right? The plane is given by 2x minus 3y plus 4z equal to 2. And the normal vector to the plane is given by 2, -3, 4. Right? You just grab the coefficients from x, y, and z. And so this equation always ends up being, it's your PS dotted with your normal vector, absolute value, divided by the magnitude of your normal vector. That's your distance. And then if you have to find distance between any other things, it's really these equations. So for example, someone could ask you to find the distance between parallel lines. But really, if I want to find the distance between parallel lines, you know what that really is? It's the distance between a point on one of those lines and the other line. Right? And so then you just use the point to line equation. You just have to find the right pieces. Yeah. No, so it's actually an absolute value here because this is right. When you take a dot product, you get a scalar, not a vector. Right. And so here's the thing. Here's kind of the lazy mathematician notation that I've been using. We use these absolute value looking things, and we're like, well, if the thing's a vector, we mean magnitude, and if the thing's a number, we mean absolute value. But that, yeah, if you look back here technically, so I should have been, I could have said here, if I want to use the double notation here, these should all be double notations because these are all magnitudes of vectors. So should this. So should this down here. And so should these over here. These are magnitudes of vectors. These are magnitudes of vectors. So far, actually, the only one where it's been an absolute value has just been the one I just wrote, where it was the dot product. But you do need the absolute value there, because if the dot product ends up being negative, then you need to take the absolute value of it so you have a positive distance. Yeah, and then there's some other stuff about like finding if lines intersect or are parallel or are skew. And we can do an example of that next class if you want to. It's a straightforward process. It's just kind of a lot. I feel like that's most of it. I mean, there's a few other things, but it all kind of boils down to something like this or something like this. And then using the normal vector, to be honest. Like a lot of finding all this kind of stuff is also using normal vectors at some point. Sure. And then your chapter 13, sorry, chapter 13. Yeah, we did there's like nothing in 13. I guess we did a little bit in 13, right? Yeah. In chapter 13, we had essentially vector functions. Right, so like position, R of t, velocity. And he uses the dot notation. So R dot, which is V of t, and acceleration, which is R dot dot, or V dot, or just A. And I don't feel like we did a whole lot with this. I mean, like, and then I guess you can say speed, right, is the magnitude of velocity. But most of the stuff would just boil down to like, well, you've got these things, and maybe I'll ask you like, is acceleration perpendicular to velocity? So great, take the dot product, set equals 0. Or given some like acceleration function, vector function, and some initial conditions, work backwards to get the position function. But I feel like that's all pretty much is calculus that we already know how to do. It's just you're doing it in 3 places instead of in 1 place. I remember there used to be one particularly challenging question in this section that like gave you what felt like not enough information to start with, but I haven't seen it pop up, so I don't remember exactly what it is. But yeah, chapter 13 feels like it was a blip. And then chapter 14. So for chapter 14, yeah, functions of several variables, typically just 2. And then we have, he did talk about limits, right? No? Okay. All right. So then we have partial derivative. Not, oh my God. Sorry. Partial derivative. So here's what I would say. If you're planning on, I know that it's Caleb and Madison, if you're watching this video later, if you're planning on taking 21D in the near future, like in the summer or in the fall, come see me or Grant first so we can maybe show you a little bit more of what was happening in chapter 14, because there is more stuff. And that, not that my 21D knowledge is particularly great, but like I feel like there's stuff there that you want to have seen, because 21D, there's a lot of stuff that has surfaces. I'll also point out, Grant has spent, I think, the last quarter making a lot of really good videos for 21D. So if you're looking for a resource there, I would definitely say that's a great place to go. Okay, and then finally, so partial derivatives and then finding and classifying critical points. That's kind of it. Okay. So that's what's on the agenda for you to make sure you're feeling comfortable with.